Good morning, good afternoon, good evening, wherever you are in the world. This is David D. Hilser, and you have reached the John Chappell Natural Philosophy Society and, of course, Dissident Science, my YouTube channel. I want to welcome all my subscribers and also all the subscribers to the John Chappell Natural Philosophy Society. I'm David D. Hilser, and you've reached and you are watching live Saturday Science Chats. Hey, I've got my physics police hat on, and of course, I'm representing, and I'm one of the directors, actually, of John Chappell Natural Philosophy Society. I love this. For those of you who don't, what is this? This is a Greek letter, phi, and it turns out the reason we have that as our logo is phi happens to be the letter you have for Greek, or I think it's Greek, for the word natural and philosophy. Believe it or not, both of those words start with this. And since we are the owners and keepers of naturalphilosophy.org, and in my opinion, the best organization in the world to be called natural philosophers, which is the word everyone uses for physics and cosmology. Before there was the words physicists in physics and cosmology, they were called natural philosophy. In fact, Newton himself, that's what he was, a natural philosopher. And of course, it looks like a tree. So me being an artist kind of guy said that looks like a tree, and gravity is one of the big things we look at. So we have these T-shirts. So we get them at our conferences, and of course, COVID squashed our conference this year. But hopefully in 2021, we'll have one. And I do promise that if we can't have it in person, we will have it, of course, virtually, which everybody's being able to do. Today, it's going to be a great show. We've got John Eichler on. He's going to be talking about cosmology and expansion tectonics. I've followed John's work for many years. I'm really looking forward to this talk, so don't go away. But before that, of course, we have my announcements and news, all that kind of thing. I want to keep everybody up to date. And as you know, this is our Saturday Science Chats, and it's sponsored by the John Chappell Natural Philosophy Society and Dissident Science. If you are from the CMPS, don't know what Dissident Science is, that's my YouTube channel. I'm approaching quickly 3,500 YouTube subscribers, and I want to thank everybody for subscribing. It's vital support to our community of people who are critical thinkers. And of course, John Chappell also we have our YouTube channel. We're broadcasting live to both of those, and also the John Chappell Facebook page. So I want to welcome everybody who's watching today. And let's go on, and the spiel that I always have, but it's important to remember this because we have new people watching. What is the CMPS anyways? It's an organization that above all promotes critical thinking without malice, to be an organization that supports, publishes, and promotes serious scientific work outside mainstream science, to provide a forum for open debate about modern topics in physics, cosmology, philosophy, and mathematics, and other topics as well, to provide a forum for presenting serious papers and theories without fear of censorship, and to be run and controlled in its entirety by its paid members, including election of directors by its members. I'm one of the directors, and when people don't like me, they are going to, I guess, they can just boot me out. We do that every so often, but it's a great privilege to be part of this organization. And going on, if I can, the control room. You're the control room. You're everything today. How to participate and support. It's very important. It's your help and your contributions are vital to making this happen. This is not sponsored by some commercial endeavor, where it's not sponsored by some philanthropist. It is sponsored by all of us. So you want to support us, you can sign up on naturalphilosophy.org. Please consider becoming a member. Memberships are annual right now. Like I said, I'm going to be in January. We're going to have monthly contributions, because some people, even if you're on a fixed income and you're retired, like many of our scientists who are doing serious work outside the mainstream, paying $5, $10, $20 a month is of great help. Like I said, right now, we have our biggest payments this month, so it's greatly appreciated. If you've been watching this channel and you've been enjoying this channel, please consider becoming a paid member. It is well, it's not vital. It's actually vital. It's essential. This doesn't exist with everybody. And if you can pay more, if you can contribute more, we have other categories up to $500 and beyond. You can donate. If you just want to donate once, there's a donate button, and go for it. It's greatly appreciated. Of course, you can participate in our community discussions at nationalphilosophy.org. And also, you can post news and happenings about us on social media. I think people are starting to get the idea. Even some of our oldsters, I'm going to tell you about that, a little story about that coming up in these slides here. But it matters. This is where the world is today. This is no longer a typewriter, send out newsletters and call each other on the phone kind of thing anymore. It is a different world, and luckily we are right in the middle of it with our live broadcasts, etc. Our websites, again, is naturalphilosophy.org. That's our membership and our community. Oh, we have great conversations always going on there, and news that people post that concerns all the critical thinkers in cosmology, physics, etc. We have an online magazine called sciencewoke.org. I know it seems like people got the word woke and started weaponizing that, and I think that's a political thing. But this means science woke means, hey, people, eyes wide open, and it's no political anything there. If you want to know about what's wrong in physics and cosmology, because if you're just new to this and you're thinking Einstein's wrong, come on, how can that be? Well, go to sciencewoke.org. We have great articles by really great writers, videos, and we also have explanations and the movers and shakers in the world of critical thinking. And of course, we have a Wikipedia, wiki.naturalphilosophy.org. And I'm going to say this again to everyone, all of you critical thinkers who have a profile, or if you are a critical thinker doing work, you have a YouTube channel, whatever you have, and you are not in our wiki, you should be, because a lot of what Google will bring up about you will come up in that wiki, and you have complete control about what you are, who you are, your profile, your biography. You got to advertise yourself. Remember, no one's listening to me. Well, guess what? You can't just sit in the woods by yourself in a cabin all alone and expect people to come knocking at your door or find you. That's not the way the world works today. So if you are a member of the CMPS, have you checked your profile? Have you looked at what's written in Wikipedia? Because we have transferred almost 3,000 profiles of people from our database to our wiki, and that wiki is a real wiki. It's not a fake wiki. It's based on MediaWiki, which is the software that runs Wikipedia. So getting your profile out is very important. In fact, many of our members, when you type their name in, you can say who is and their name, this comes up. And if this comes up and you have control of it, you can put all your work there and try to get the word out about all the great stuff you are doing. And of course, we have in 2021, we will be having our first courses coming out in the Chappelle University, courses in natural philosophy. No, you can't get a doctoral yet. And yes, we founded it in 2018, but we're still building it. And we're using what's called LearnDash, which again, you have to support us, pay your memberships, because LearnDash, our website, all of these things cost money today. It used to be being on the internet was pretty much cheap, but now people realize this is the place to be, and now the prices are going up, and your support is vital and greatly appreciated. As one of the YouTube channels about SpaceX, which I love, the SpaceX stuff, says, you rock. So if you support us, it's pretty cool. I got to come up with something like that. Critical thinkers, science news. I'd like to do this every week. I try to grab stuff that grabs me during the week, and there's always stuff going on. And here's some of it. Here's some of the discussions. You can see me here getting in on that, because I see these things. I go, I can't keep my mouth shut. So we have new people signing up, and you can see, how does Earth get its additional mass? You want to discuss that with people who have been thinking about this for a long, long time, or even new people, and you want to get in there and give your 2 cents worth, go to our naturalphilosophy.org, and you'll see in the activity feed what's going on there. So there's articles, and you can chat, and we have many groups, and you can bring up stuff that you want to talk about. Now, this is way better than those email chains. I get those all the time. I feel sorry for everybody on there because it's sort of lost. It's not lost when you do it here because they're in groups. People can find them. They can go to the groups and the forums and see topics, and they can, and those get indexed, of course, by Google and the other search engines, and they come up. So that's happening. Fractal woman, Lori Gardy. She's into fractals. I love her work. She's put out a couple of videos, one 6 days ago, about a week ago, on relativity. So if you are one of those people who don't believe relativity is true, which is most people these days who are critical thinkers, then you want to check out her website. You can just look up Fractal Woman, and she's put out some really nice websites. My gosh, she passed me. I mean, she's passed me a while back. She's got over 4,000 subscribers. And oh, sorry about that. It's a good thing. No, I don't have COVID. I've had several blood tests, and those blood tests here in the United States give us an indication of whether you even had it. Haven't had it. Eat healthy, whole plant-based diet. That's what does it. Okay. Another person, Ray Fleming. He is also a member of the CMPS, and he puts out 15 reasons mu and tau neutrinos don't exist. I'd even go further and say my mentor who got me all into this is neutrinos don't exist at all. But, of course, if you don't believe that, well, then check out things about the neutrino. But the neutrino is the bad boy of particle physics. People try to use it, especially in the distant world, because they're looking for that elusive ether particle or something like that. Be careful, folks. The neutrino was invented, and it is a crazy idea. It's just not something, in my opinion, a lot of people's opinion, that even exists at all. But it doesn't matter, because Ray is talking about why the mu and the tau neutrinos do exist, and he gives some really great videos on that. And oh, by the way, please, with Ray and with Lori, go to their YouTube channels and subscribe. And like their videos. Even if you don't like, if you don't like it, put a thumbs down. That's fine. But you participating and subscribing to these people is the way we support our own work. I try to get that through people's heads. Like and subscribe to our YouTube channels. Like and subscribe to Critical Thinkers YouTube channels. Even if you don't agree with them necessarily. What we need to do is support each other in our endeavors. And Ray is out there putting it on the line. He's now got 76 subscribers. He didn't start very long ago, and I'm hoping some of you have gone there and looked up Ray Fleming and put in neutrinos right after that, and you'll probably come right to his channel and Ray Fleming. Give him some support, vital support, by subscribing. The more subscribers a person has, the more YouTube's going to put those in front of people when they type in something about, for instance, relativity or physics or neutrinos. His stuff will come up. We've got to support each other. If you are a person who thinks no one's looking at my work or no one's paying attention to us, well, the reason is we're not paying attention to each other. We have to band together. That's what we do when we have our conferences. That's what we do in our organization. That's why we have YouTube channels like Dissident Science, so that we all get together, subscribe to them, like them, dislike their videos, but participate. It's very, very important. My dad, the particle guru, you can go to youtube.particle.guru, not .com, .guru, and he's getting close to 400 subscribers. He just put out a couple of videos. Why are the planets on the same orbital plane? Oh, lots of people have talked about that, but he's talking about that with TPM, the particle model, and also the TPM black hole, because our model of the universe, we have because we have a model for everything, we can tell you why there would exist a very dense object that is not luminous. There are no waves of particles in our model coming at us. So very interesting. Again, go to his channel. If you haven't supported my dad's channel, I mean, come on, that's my dad. No, no, he's actually very interesting. I love him as a scientist, actually, very methodical. He's much more controlled, much more methodical than me, who just goes in 17 directions at the same time, and it seems lost most of the time. But anyways, again, go to his channel, subscribe. If even if you don't want to watch it and you like him and he's a nice guy, hey, support him, give it a thumbs up on his, because all of those things matter, right? Also, very good. We're lining up people. And oh, by the way, I do want to thank Franklin Hugh for sitting in last week. I just didn't have anybody. I got busy, sort of let it go. And Franklin stepped in and actually had a very, very stimulating conversation about the shape of a photon. So if you haven't checked that out, go and check out our YouTube channel. for the CMPS, John Chappell Natural Philosophy Society, and take a look at that, and you're going to be able to listen to a very stimulating discussion about the photon. He has a very interesting shape that he thinks it is. Of course, this is all open. I mean, we're critical thinkers. We can think the way we want. And that's what's great about our channel and our community. But coming next week is the infinite universe theory. And we're going to be talking to one of the great scientists of our time, Dr. Glenn Borchert, and how he has taken Newtonian mechanics and moved it into the infinite universe theory, which is my dad and I's particle model is absolutely based on his neo-mechanical infinite world. But this will be really interesting. If you can check it out, we've had a couple of conversations with him. Check out our interviews and talks with him. But this one, he'll be giving a talk on it and about his book. Check it out, his book. You can get his book online, Infinite Universe Theory, on Amazon. Check him out. Oh, and we have more coming. Yes, one of the great friends of the CMPS and an absolutely just amazing guy. And when it comes to being a critical thinker, he is Dr. Alexander Unsker. He is the author of a book that everyone in science should read. I mean, everyone, called The Higgs Fake. You will find in that book the shocking, I know it's going to be shocking, probably to all the people who've looked at particle physics and who are dissident thinkers, dissident scientists, and critical thinkers. It's not so shocking, but the truth of the matter is the methods to which they go about finding a particle using the Large Hadron Collider, or any particle, is absolutely stunningly bad. If we were to take scientists from NASA or engineers from NASA or engineers from SpaceX and put them in the place of the engineers and scientists at the Large Hadron Collider, and then let those people explain how they go about their science, they would be ridiculed. Those people would probably turn their backs, walk away, and say, keep finding unicorns, because what you are doing is not scientific, and nor is it science. The way they go about finding signals for like the Higgs boson is shockingly bad. And if you haven't read The Higgs Fake, and you are people believing that there is a Higgs boson, if you're people that believes there are quarks and all these other particles, the Z particle and the W particle and all the things that they supposedly discover and then give them Nobel Prizes and pat themselves on the back, well, you need to read The Higgs Fake. Dr. Alexander Unsker is one of the brave voices out there who takes on the physics community, and he has a doctoral degree in physics, and he's from Germany. But he is a brilliant mind. Having conversations with him has always been a joy. I've had, on Dissident Science, a number of years back, I've had conversations with him, and they always are super stimulating. And we can have him on. And of course, we'll be live, so you'll be able to talk with him and ask him questions live. He's also the author of Einstein's Lost Keys. And if you're from my Dissident Science channel, you know that I've done a couple of videos. Check it out, Dissident Science, Alexander Unsker, and you'll see a couple of things. But we're going to have him on. He's promised to come on our Saturday mornings show and talk with us. And not only that, I got another person coming in January, or at least whenever we get him, and that is the Nick of Time, Nick Percival. And I love him. He has a channel. So what do you have to do, my little minions and friends and critical thinkers out there? You go to, type this in any browser, youtube.nickoftime.guru.com.guru. It'll take you to his YouTube channel, and you press the subscribe button. He's over 200. He hasn't put out a video for quite a while, but he's got a ton of videos. They're super interesting about special relativity. This guy is from Harvard. So those people who think that we have people who are just like, janitors and car mechanics, believe me, we don't care who you are. Like I say in my movie, Einstein Wrong, it's don't listen to me, listen to what I say. What does that mean? Don't listen to me. Don't listen to me because I have a title, because I'm a science evangelist on TV to profess to understand and be all things paradoxical, impossible to understand, and then try to communicate that to the world masses. No, these people are, like the Nick of Time, these people are real, true critical thinkers, and they are out there talking about what special relativity is and taking you step by step about what the problems are. And Nick is really good at that. And he is, it says right here, Nick, your time guru, saving scientific souls in the nick of time. Look at the marketing we have on there. Who did that? The guy must be a genius. Well, I don't know. Anyways, check it out, and please subscribe to his channel, folks. I want to see the subscriptions go up to his. Again, you don't have to even watch his videos. You know he is a critical thinker. You know he's supported by many of us. Go in there. That's how you do it. It's real easy, folks. Just takes a few seconds. Do it for us, and we're going to be talking to him, so that's going to be absolutely great. And of course, now we are getting to our person who's been patiently waiting. He has been in the area of expansion tectonics, and he's going to be talking about cosmology and expansion tectonics today. That is John Eichler. And John Eichler graduated from the Illinois Institute of Technology and worked for the IIT Research Institute for 8 years. He has worked on computers since vacuum tube days. Hey, he's in the same generation my dad, who actually worked on the Univac. Hey, John, I don't know if you knew that. My dad worked on the Univac computer, walking around changing tubes, telling me all kinds of stories. I don't know if they must be, if they're true or not. They are true, I'm sure. So he's worked since the vacuum days doing both systems programming and digital analog design. He's a computer scientist like me. Computer nerds. He designed blast shields for nuclear reactors for the U.S. Atomic Energy Commission, and he has in many other fields. So you can imagine, you can sort of get an idea of why he is a critical thinker, and maybe how he, we'll have to ask him about that. But we're going to have him, he's going to be giving a presentation first, and then afterwards we'll be able to have a conversation with him. He's currently working in the area of expansion tectonics, and that's why he's here. And I have the next slide to remind me to play the bumper that I always make, or the stinger or bumper, a lot of different words for it, but we're going to do that, and we're going to bring him on. Finally, I'm remembering to do that. So let's bring him up. There he is, John Eichler. How are you today?
Good morning, David, and how are you?
I mean, I cannot believe it. I was talking with you just like my dad. My dad's 83. I looked at you, and you said you laughed when you found out I was 61. I looked at you and I said, oh, he must be in his 60s as well. 81. I mean, you are like, do you credit that to your critical thinking mind? What do you say?
No, I'm just too lazy to do anything, so I just sit around and age.
And but you don't seem 81. You're much better than the politicians at your age, for sure, in the sense of those guys seem to be having problems. But I want to thank you for coming on here.
What computer Univac did your father work on?
Oh, well, I will find that out.
I did on the 1105.
Okay, I will find that out in fact, what I'll do is he's probably watching. Maybe I'll have him join us and come in. We'll find that out. Yeah, he talked to me about, I think it was in Utica, New York, I think where it was, but in the early 60s, I believe, and he would walk around with, replacing vacuum tubes. They were in like banks of 8 or 16.
Many a night.
Oh, man, we're going to bring him on. I'm going to make sure he's on.
1960 census was processed on 3 Univac 1105s. One was at the University of North Carolina. I don't know where the other one was, but the other one was at IIT Research. Back then it was called Armor Research Foundation.
And where was that located?
In Chicago.
Okay, so my dad must have been with the other one.
Well, I don't know if it was the same computer.
Oh, yeah, it could have been, yeah.
Computers, but
right.
That was a mammoth machine. What I grew up on, I absolutely loved it. It had a cycle time, I believe, of 250 milliseconds.
Oh my gosh.
No, it must have been I'm sorry. I think it was 250 nanoseconds, which would be a quarter of a microsecond. And it was slow. To transfer one location to another location, it took something like 18 microseconds. And that was a fast instruction. It had no internal timers. I'd love to chat with your dad sometime about the thing.
Oh yeah, well, like I said, I'm going to have him bring him on while you're giving your lecture. I'll make sure he comes on and we'll have some chats about that because we're all, in the end, people who like science. It's all pretty nerdy, but yeah. So I'm going to just give it over to you. I'm going to put your let's see. You want to get your slides ready there for us? I think we need to do that there because I'm seeing I think something else. It's your screen, but I don't see your slides there.
Okay,
So
let me.
okay, so he'll be getting his slides up. He's going to be talking about a
There we go.
course.
Can you see that?
Not yet. I don't
Okay.
see it.
Hold on.
Again, be patient with us, everyone, because it's not always easy to do these
Can you
things
see
pretty
that?
long distance. No, it's not coming up because there I see something coming up. There it is. I see the screen, but I don't see your slides yet. Now I see your slides. You can make those full screen for us. And then slides, there we go. And the floor is yours. There it is.
Hold on a second. I'm going to get my slide back up here. There we go. Okay, today I'm going to talk about cosmology and expansion tectonics. There's a connection, and my feeling has always been you have to know something about how the universe was put together is to understand what's going on with the Earth with expansion tectonics. The topics I'm going to discuss.
John, I want to. There's a hide button. See that below on the screen. Just put that hide there. Whoops! What? Oh my gosh! What happened there? That's weird. Yeah, it was supposed to be hide, but go ahead and try that again. I'm sorry.
Oh, that's okay.
Because that gets that out of the way. But once you get it up there, you should be able to hide that. But don't hit that on your side, I guess. Sorry, folks.
Can you see it now?
No, you're gonna have to do it again.
Oops. Okay.
No problem. And I'll stay away. Don't hit that because usually that will hide the little bar there, but it seemed to hide your whole thing. So, my bad.
Hold on one second.
Should let you go. So, anyway, we're here with John Eichler. He's going to be talking about the cosmology and expansion tectonics.
Can you see the screen?
Not yet. It's coming up almost. So as soon as he gets that screen, yep, I see the screen. Go full screen, and we'll do this one more time, and get that up full screen and in slide mode, and we can go. Not quite there yet. Again, there we go.
You see
okay.
the,
I see it all. I'm just waiting till you get it. There we go. There we go. And the floor is yours, and I will shut my mouth, leave that thing where it is. And again, apologize. Why don't you start there again?
Oops, here, let me move this thing. Oops. Yeah, let me move that thing over.
Okay. Yeah, that little hide button should hide that little thing, but leave it there.
That's I'm going to leave it there. Yeah.
Okay. All right, John, let's start over. And I apologize, everybody, but it's worth it. Thank you, John. The floor is, again, yours.
Okay. The topics I'm going to discuss or touch on: one, development of new concepts in science, the importance of the laws of physics, cosmology, and here I'm going to talk about gravitation versus electromagnetic forces, galaxy formation, and solar system formation. And then I'm going to talk about expansion tectonics and the uniqueness of the Earth. Okay, in my opinion, there are many areas, and I'm sure that most people watching this would also feel there's a number of areas in science where we feel we understand something, but in reality don't. One of the reasons for this is because where you can have something that you can do a hands-on observation and experiment in a lab, you can come up with repeatable results. But so many of these things, like this Earth, and when you go out in the universe, you have no direct hands-on. You can see the light, you can analyze the light, you can tell the motion, what have you, but there's no really hands-on. It's not possible to do hands-on laboratory experimentation. However, we must remember the strongest evidence is where the laboratory experimentation backs up the theoretical constructs. There's a lot of theoretical constructs out there that people have come up with no laboratory experimentation to back it up. And deriving concepts from observations depends on how the observers' observations are interpreted by the observers. In other words, their world view. And getting into the laws of physics, one should always question when new ideas, anybody can have new ideas, but once the new idea comes out, one should always question any proposed new esoteric laws. And I love the word esoteric because so many of these concepts, unless they're explained or examined in a laboratory, are theoretical concepts that have no basis in science. So one should also question any concept that does not have empirical or experimental laboratory verification. Just because a concept can be visualized doesn't mean it follows the laws of physics. There is no evidence to indicate the laws of physics aren't valid everywhere throughout the universe. Known laws of physics are backed by empirical verification. And almost every law of physics that I know of actually has some kind of empirical verification, either laboratory or experimental. And known laws of physics must be obeyed. Now, there is possible there are laws, and very probable there's laws of physics that we don't know. We know a lot about it. We spend many centuries studying physics and the laws of physics, but it's possible that there's a law out there that we don't. But you have to have some type of verifiable experimentation. It's no good to propose some kind of abstract esoteric law without having verification. Now, a few words on worldview. My definition, worldview is what the scientist brings to the table. His or her paradigms, which are mental concepts of how the universe works. Have a typo there. This is important since it affects our observations and our interpretations of those observations. In other words, your worldview, you have certain built-in paradigms from classes you've taken, from books you've read, and you have a certain internal visualization of how the world works. But and this really affects the way you view the world. For example, to a hammer, everything looks like a nail. Paradigms are like two-edged swords. They assist in our cognition of the world around us, which is very good, because if we had no framework to go by, we would have a hard time understanding what the world is. In other words, if you have a concept of gravitation, then you could understand why houses sit on the earth, why when you drop something, it falls toward the center of the earth. You have to have some type of a concept. But the other edge of the sword is, yet they hinder us from looking outside the box. And very often, science disciplines will get into the situation where the mental framework that a person has dictates what they see. Like to the hammer, everything looks like a nail. So when you have a concept that's built in, then when you look at everything, you interpret it as a nail. In other words, scientists who, before relativity came about, scientists looked at the world through Newtonian physics. However, when relativity came around, they had to adjust because their inner paradigm would not accommodate the new reality of physics. Now, I'm going to talk a little bit about cosmology. And when I was doing my thesis, I just happened by accident to run across a book in the university library called Evolution of the Solar System. Because I'm writing a book, I've got the book almost written, and it was about the universe. And I found this very interesting, and I started to read through it. It was written by a man by the name of Hannes Elfven. Now, Elfven's big claim to fame is that he is known as the father in the field of plasma physics. He got a Nobel Prize, actually. And in fact, there's a funny story about that. The Nobel Prize he got was for a concept. He came out with one concept of frozen in lines of magnetic lines, and this concept of frozen lines. Everybody in the field adopted that and thought that that was really great. And about 15 years later, he realized that you could not have the frozen in lines. And but they gave him a Nobel Prize, and his Nobel Prize lecture was about how they're giving him the prize for something that he knows is false. Very interesting individual. He actually, Elfin, was one of the few members of not only the United States Academy of Science, but the USSR Academy of Science. Very, very brilliant man. And I have a few of the things down here. He's written lots and lots of articles, but he back in 1942, he wrote a book on the formation and evolution of the solar system. It was only, I don't know, 45 pages long or something. It was just almost like a brochure. And then in 1954, he wrote another book called The Origin of the Solar System, which is a thicker book, maybe 150, 200 pages. And then NASA employed him and this other scientist by the name of Arenas, they employed him for 7 years to work on another book for them. And he came out with this evolution of the solar system, which was the picture that I had just shown you previously. And he looks at everything. His worldview is plasma, magnetohydrodynamics. Everything works there. Gravity comes in to some extent, but it's not really one of the prime formers of the solar system. So no, he was talking about gravitation versus electromagnetic sources. The current paradigm is that gravity shaped the universe. It shaped the galaxies, it shaped the stellar bodies, suns, etc., and it shaped the solar system that we have. Alphin's paradigm, his worldview is plasma physics and magnetohydrodynamics, as well as gravitational forces, shape the universe. And he proposed, and this was way back in the 50s, he proposed that there were enormous plasma currents flowing in space. Normally, when you're thinking of an electric current flowing, you have to have a wire or something where it's flowing in. I mean, that's what we find out here on Earth. But he proposed, he said, in space, there's got to be a tremendous current flow. And the plasma currents don't need any kind of conductive media. And then he also proposed the foundation of this concept of his about satellite and solar system formation is he wanted to develop a general theory of the formation of secondary bodies around a primary body. In other words, the theory, if it worked for the formation of planets around the sun, the same thing should work for the formation of satellites around planets. And this was his big thrust of all of his different books and things. Now, from the standpoint of galaxy formation, he was talking about plasma currents in space. Prior to us sending up spacecrafts, very few people thought that currents in space were possible. Alphin hypothesized that there were plasma currents in free space. And the proof of plasma currents have been verified since by space vehicles. Sometimes the space vehicle will at one time have no voltage potential across, and then just a second later will have thousands of voltage potential across it. Such currents produce extraordinarily large electromagnetic fields. And a man by the name of Anthony Pratt at one time did, and Pratt, by the way, is a brilliant plasma. He was actually a student of Alphin's. And he worked out at Los Alamos, where they were doing all kinds of works in plasmas and this type of thing. Well, they have fancy on their high-speed supercomputer out there. They simulated these currents, And the currents were like, I mean, if you think of them almost as two pipes, or each current would be like one pipe, but these pipes to form galaxies were like 300,000 light years across and had 10 million trillion amps. The reason it has so much amperage is because you had so many charged particles moving. And then when such currents like these can interact, they form galaxies. And he's scaled these things based on laboratory experimentation. One of the things which Alphen and Pratt were very careful about is scaling effects. And if you have something on one scale, how do you actually go and scale that up to larger scales? And so a lot of their work was done on how do you actually go and you scale these things. So he could apply the same rules that he found in the laboratory here on Earth in studying plasmas to currents in space. And a fellow by name, well, Pratt did this deal over here. I'll explain it to you. You have electric currents coming in. Now, those currents charges always go to the outside. So the charges in them would repel, and you'd end up with one side of the current having mainly positive charges and the other side negatively charged. And when they would come together, they'd actually go and wind around each other. And the flow is from here on down to here. Now, Pratt did these computer simulations, and this is his results, or a few of the pictures. Starts out with the two corresponding, and then they come closer together. Then they start intertwining like this, and they intertwine more and twirl around. And he went and then looked up Alton Harp's galaxy atlas of peculiar galaxies, and he began to see that's exactly what people see, which gave him oops. My connection was lost. Let's see if I can get it back. There we go. And so these are illustrations of actual galaxies that look exactly like Pratt predicted or found with his computer simulations. Now, Eric Lerner is a very interesting fellow. Yeah, I've met him and communicated with him some. And he wrote this book back in 1991, I believe. The Big Bang Never Happened. Very excellent book. If you can get a copy of this somewhere, is wonderful. And Eric was working on a PhD in physics, and then he got waylaid and never finished his PhD in physics, but he was very mathematically oriented and physics oriented. And he wrote this book, and in the book, he explains in great detail how this whole process works of these interacting currents in space. Okay. I just showed that how his computer simulations and Lerner's theory show how these forces. Output shows typical shapes of galaxies. Two other important items were found. Lerner calculated based on how these currents would interact that he could tell what the spacing of objects were in space. Stars are typically have a spacing of 10 million times their diameter. Galaxies, 30 times their diameter. Clusters by 10 times their diameter. Eric in this book explains all that. Is a very interesting book if you get your hands on it. And also, and this is quite important, there's abnormal stellar velocities around galaxy centers. And let me see if I have, in other words, and I'll show you in the next slide. A gal by the name of Vera Rubin, who was a famous American astronomer, who just died, I believe it was earlier this year or last year. And she took galaxies and actually found the velocities, the galaxy rotates around. So you can, if you take a galaxy and look at it sideways, so it looks flat to you, you can take measurements going out and tell what the velocities are going out further and further from the center of the galaxy. And on one side, the velocities, if you look at, they're done by the red shift. If you look at the stars that are going away from us, they are experiencing a red shift. And if the stars are coming toward us, they have a blue shift. Now, this threw the whole thing into confusion. And on this next slide, I'll show you, but the result is that no dark matter is needed because of Pratt's computer simulations. He found that the velocities of the galaxies as you work your way out actually go right according to what is observed. And here's some of Rubin's work. Here's the center of the galaxy. And you take the shift over here, and on one side, you're going to get a red shift, and on the other side, you're going to get a blue shift, depending on which direction the stars are rotating around there. And normally, if you have a system like our solar system that follows Kepler's laws of orbital laws, if you go further away in order to keep into orbit, the body goes slower and slower. In other words, Mercury goes faster than Venus, goes faster than Earth, goes faster than Mars. Each body on its way out will go slower because it's further away from the central source of gravitation. But what she found was, and this is this galaxy, and it comes up, but it doesn't go down. You'd normally expect it to go down almost like an exponential decay, like this. And it didn't. And here's another galaxy, and she found it went like this, and she plotted the red shifts. Here's another galaxy that went up like this and goes out. In other words, if you get way out here, the stars are moving at the same velocity that the stars are closer in toward the nucleus of the galaxy. Here's another one down here. So the stars way out here are moving at the same velocity almost as the stars right next to the center. When people saw this, they said, hey, this is impossible. And consequently, what they did, they, like so many times in physics, people like to add fudge factors to make things come out nicely. And the fudge factor they added was dark matter. So you had to have, in order to explain this, according to Kepler's laws, you have to have more mass in the closer to the center of the galaxy. And consequently, this Pratt's simulations showed exactly what is seen. So, which brings really the question: if you view it according to the Newtonian gravitational standpoint of Kepler's laws, this would be abnormal. If you view it according to the laws of plasma physics, this is the natural result. Now I want to talk about solar system formation, which is kind of an interesting topic. Lunar spacing for suns is typically 10 million sun diameters. Now the process starts out this way. You have these suns, and the suns are, 10 million times the diameter from another sun. Now, they're not, I mean, this is on the average, but it's not always exactly that. But you can imagine the sun as having a huge sphere around it, and the sphere is 5 million sun diameters on either side to give you this whole diameter. Now, once the sun begins to start, in other words, when this process starts, you have material coming in, and it does it by gravitation. It collapses into what becomes our sun. The mass of the original sun is so large, even a relatively slow-moving rate would produce high angular momentum. Now, as the sun it forms, it is rotating. And this rotation produces a very high amount of angular momentum. And in physics, angular momentum is one of these things you have to conserve. And studies that have been done, one computer simulation, showed that the original sun had to have about 2% of deuterium when it was first forming. Not a whole bunch is known about the early sun formation, but it turned out that with the computer simulations, if they just used hydrogen or helium, they weren't getting the results that they needed. So it turned out that deuterium was in and it was used. And this is a solar radius. And now these are not geological times, but it took about 200 million years, 250 million years or so for the sun to form. When it first formed, it was much larger in diameter than it is today. Then it came down, and then when it was burning the deuterium, you ended up with a smaller, yet still hot sun. And then when the deuterium was gone and it got down to burning helium and the normal fusion reactions that you have, the sun came way down until it was much larger in the beginning, but it took a couple 100 million years for this to occur. Now, Elfin had this heterogonic process. And this is what he called it. And the word heterogonic came from the Greek words for companion and generate. Now, once again, going back to what I said earlier, what he was after was a theory that would not only explain the formation of the planets, but also the formation of the satellites around the planets. This is a very big problem in the old Laplace galaxy, where solar system formation, where you had dust. The dust came down and formed the planets and everything else. It doesn't work. There's a whole bunch. If you pick up Alfin's book, which is incredible, it's quite mathematical, by the way, which it should be for a plasma physicist. But you'll notice that he goes into many different examples. He'll tell you why this can't work or that can't work, because it violates the laws of physics, which is one of the reasons I like it. And this heterogonic process basically starts out, you have a cloud source, you have a central body. These form what's known as a jet stream, and from the jet stream, you form a secondary body around it. In other words, you have to have the central body before you do this. Now, this is kind of the general process. The sun, and Alfin will maintains and will tell you right up front that we don't know a lot about the early sun. But once the early sun formed, then you had jet streams forming around the sun, and those caused the planets. In the same way, you had around the planets a source cloud formed around the planet. You had jet streams, and those produced the satellites. Now I'll get into this a little bit more in detail. Okay, the sun had a strong electromagnetic field. As gravitation attracts further out particles, their incoming velocities keep increasing with the potential energy converted into kinetic energy. When the particle reaches a certain critical velocity, its kinetic energy becomes greater than the energy of ionization, and the particle ionizes, throws off an electron or so. The ions are then stopped by the sun's lines of force. And I'll show you in a second how this works. The rotation of the sun moves the particles in the same direction the sun is rotating, and this is called magnetohydrodynamic transfer of momentum. And remember, momentum has to be conserved. The sun is so huge, it has so much momentum. This results in the particles gaining momentum that the sun loses. Those particles speed up and by centrifugal force move down toward the equatorial orbit along the sun's lines of force. And this results in rings similar to Saturn's that surround the sun. And these rings accrete to eventually become the planets. Now, to show you how this works, here's Alvin calls these jet streams, and where the planets and satellites form. What you do is you have incoming particles. Here we have a particle A and B. As those come in, you get faster and faster because their potential energy is turned into kinetic energy. They eventually ionize. But the sun's magnetic field will stop that ionized particle, like B. And some of the ionized particles are so far up that they will go into the polar regions of the sun. But out further, you end up with these particles coming in, and they're ionized and they're stopped. The same way as if you tried to take two magnets and put both north poles or both south poles and push them together, they are repelled. The lines of force from the sun will actually stop these particles. And here's the equatorial plane, by the way, of the sun. Now the shell density, and once again, the shell density is you have these particles stopped. I mean, they're essentially like suspended out in space because they can't get through the magnetic field. The shell density is about the same as the solar corona, which is 100 to what is it, a million or so, or more. I guess it'd be more, maybe 100 million. Okay, articles per cubic centimeter. Now to compare that, our atmospheric particle density at sea level is 10 to the 19th particles per cubic centimeter, which means that our atmospheric density is about 10 billion times greater than this plasma, the shell that has formed. You can see through it. I mean, it's not, I mean, it's the same way you see through air. I mean, this is 10 billion times less dense. And interesting part about this, that the sun in one of these spheres where the particles are stopped cannot support the entire mass of a planet at once. So this is a process. It's not an instantaneous process. I mean, these particles come in very, very less dense. And as the process goes on, they're continually fed by more particles coming in. And this guy by the name of Ferraro, who had a theorem back in 1937, he says, all parts of a magnetic line of force in a conducting medium will tend to move with the same angular velocity. If there's a difference in angular velocity, magnetohydrodynamic effects will be produced, and the result will be transfer of momentum. Misspelled it again. Okay, now what happens is that the sun, the particle stops out here. The sun is turning. This particle is in a line of force, magnetic force from the sun. What happens is that the particle begins to gain velocity. In other words, the particle's momentum begins to increase, which in turn makes the sun's angular momentum decrease. And this is how you get these particles moving. Now, once the particle is moving, you have another set of forces on it. And that's the centrifugal force. And the same way as if you take a rope with a baseball at the end of it and start twirling it around, pretty soon that will go toward a flat plane. In other words, the particles go down lines of force as they gain centrifugal force, and they head toward the equatorial plane of the sun. Now, this slide is a little bit complicated, but let me explain to you what goes on. Here you have the sun. You have the particles. Now, once again, this is looking at it from the standpoint of the equatorial plane. You're on top of the sun, 90 degrees above the plane of the planets, and you're looking down. And what happens is you have these ionized particles, and the ionized particles come down and go into essentially an orbit. But once again, they're controlled by magnetic forces, and these various orbits, they will tend to get together because as particles go around so this is really a plasma. This arc is a plasma. As they go, the particles come through. They have all kinds of magnetic and electrical lines of force, and these tend to make a plasma. It's called a pinch effect. They tend to bring the plasma in. Now, as this is going on, and this plasma ring is being added to all the time. As this is going on, some of the ionized particles become deionized. In other words, an atom will gain an electron that's out there. Now it is neutral and is no longer affected by plasma physics. It's affected now by gravity. And the particles come off, and mathematically, I'm not going to go into any of the math here, but it turns out they will form an orbit with the eccentricity of 1/3. And then here's one place where the particle comes off. Here's another place where the particle comes off, and they begin to form this cloud. But it turns out that the cloud, the various particles will intersect at different points, and at 2/3 of R0, which is the original radius, they will condense, and they will form. It's almost like this is what Elfin calls a jet stream. They're non-ionized particles, and they just go into a Keplerian circular orbit. And he goes into all the reasons why they do this, if you want. I mean, all the orbital mechanics and all this stuff. Here's the different, these are from Elfin's book. Here's the central body. Here's the infalling gas. Some of it will go in at the top, because actually the centrifugal force of the particles up here, the gravitational, they aren't powerful enough to leave, and the gravitational force will actually, whoops, sorry about that. Let's see if I can go back. There we go. The gravitational forces will actually pull them in. Other particles will come down, and they form, it's almost like a cloud. And the other particles will come down along the equatorial line, and they will gain momentum from the sun. And here are the jet streams that are set up where the planets form. Now, what he found was there's this critical velocity where you get ionization. And it turns out that Elfin, I mean, these are figures that are, you found in the lab. I mean, is what type of criteria you need for ionization of the different particles. And there's several groups of them. There's the A cloud, because these clouds form like how far out you are. These clouds form, and they are of different materials. Now, it turns out that the B cloud, which is the close-up one, was the one that formed the terrestrial planets, and it is different composition. The C cloud are the ones that form the giant planets, and then the D cloud is thought that the D cloud was in the formation of Pluto. And because of, and once again, I can't go into all, it's impossible to go into all of this, the mathematics and everything of the book. But it turns out that one of Elfin's students worked it out, and it turns out Mercury, Venus, and the Earth and Jupiter started forming early, and then the Moon and Mars and Saturn later. And then it was unknown how much later that the Uranus, Neptune, Pluto, and Triton. Now, Triton is important. I'll get to that in a second. So here's the primary bodies in the solar system. Here's the B cloud, which formed along with some of the A cloud, formed. Here was that Mars, the Moon, Earth, and no, is this Mars? Venus, I guess it is. And then we have Jupiter, Saturn, and Neptune up here, Uranus down here, and Triton. Triton is a special moon. Okay, it's a special body. I'll get to that in a second. Here's Pluto way out here. And so anyway, this is the general scheme that Elfin finds, mathematically falls out, and it's pretty close to what we actually observe. Now, he applied this heterogonic mechanism to not only the planets, but the satellites. And on this chart, here are the clouds. You can see the three clouds here. Going around the sun, he had Mercury, Venus, Earth. They formed in this B cloud. The C cloud formed Uranus, Saturn, Jupiter. Neptune is right at the border, and so could have some of the D cloud coming in. And there's some reason for this, because Neptune is a little bit bigger than Uranus is. And Pluto's out here. And this Triton is now a satellite of Neptune, but it formed out there. And then he applied the same thing over here. This is the surface of Jupiter. You can take the same exact mechanism, because the bodies, Venus has no moons, has no magnetic field. Okay, the Earth has a magnetic field. It has moons, and I'll get to that in a little while. Uranus, each of these clouds, when it comes into around a planet that has a magnetic field and is rotating, the clouds will form satellites. And this is one of the beauties of his scheme, because he can tell from the standpoint of what type of satellites form. He can go and for what the clouds are, he can go out there and actually calculate what the mass of these satellites are. And the same thing over here with Saturn. There are certain satellites that are formed with different clouds. He gets over here to Earth. Earth had some satellites form. Mars, it's very questionable whether its two satellites were asteroids that were captured or there, because Mars doesn't have that much of a magnetic field. But this is the scheme, basically, that Alphen devised. And starting in 1939 or 40, whenever he started on his first stuff, up to the time he worked with NASA, this is the scheme that he has, and he tells you the physics that back up what he's talking about. And when Alphen doesn't understand something, he'll come around and say, well, this is unknown. We don't know this. Our best guess is, and what have you. But this is based on the critical velocity. These clouds break up according to critical velocity. Now, this is very interesting. The way that these two curves show his planetary interrelationships. This curve deals with the terrestrial bodies, and this curve deals with the giants, Saturn, Jupiter, Neptune, what have you. These are theoretically calculated curves of his. So what he did, he found that the bodies, Jupiter and Saturn and Uranus and Neptune, he found the relations here and plotted up where they fell, and they fell pretty close to this line that he theoretically would expect them to fall on. Over here, these are for the rocky planets, and he comes in, and one of the advantages is, since he's doing this for the satellites over here, he can go and take if he knows Titania came from this would be what the this is D cloud, I guess. If he knows it came from here, then on this chart he can put it in. So he can put in the various satellites to find out how the theory would work. And this is in his original book of 45 pages or so that he did back in 1942. He found that everything worked out except for this one dot. And that one dot represents Earth. And he couldn't figure out why the devil Earth would be over here and so widely variant from all the other planets and satellites that fell so beautifully according to the theoretical curve. And he mentions this also in his 1954 book. He says, as the Earth-Mars dot is the only one which does not fall on either of the curves, one must seek the cause of this exception. We should expect it to fall on the second curve because the Earth and Mars are both inner planets. If we suppose it does so, and further assume that there's no error in either the Q value, the graphs that I just showed you, this is one of the parameters in there, or the mass of Mars, we can calculate what the mass of the Earth ought to be. The mass we find agrees with the mass of our moon. What conclusions might be drawn? And he actually, the bolding I did, but he actually italicized that in his book. What conclusions might be drawn from this is difficult to say. The moon's large mass and large distance from Earth have already shown that it is no ordinary satellite. Instead, the Earth and the moon form some sort of a double planet. Now, what I feel, and based on James Maxwell's work with reconstructing the earlier Earths on the expanding Earth, I think that he actually, the mass of the Earth was probably less than. And Alfred had absolutely no idea, I would assume, that anybody in their right mind would think the Earth was expanding. And so the mass of the original one, I mean, he was using for that graph, he was using the mass of the Earth as it is now. But the mass of the Earth, to me, it's not definitive proof, but it's a very good indication that the Earth was indeed smaller, where it would fit closer on this line. Whoops. This is a strong data point that at one time when the Earth was formed, it was smaller and later expanded. Now I'm going to talk about the moon formation. There's a thing called a Roche limit. What happens is if you have one body over here and a second body, and they're both held together by their own gravitational force, if that body comes into the Roche limit, the gravitational force of this body coming in would not be strong enough, depending on how big the body is, would not be strong enough, and it would be pulled with like a tidal action and pulled off and actually broken off into particles. And pretty soon you'd end up with nothing but particles. This is kind of hard to see on this diagram. But if you have a moon that comes in and it passes the Roche limit, it will be pulverized. Not down, necessarily in grains, but it would end up by pulling apart. I've seen some calculations that are done, say maybe break into 1,000 parts or something like this. But keep this Roche limit in mind. It applies to bodies big enough to be gravitationally held together. Optic, there was a guy by the name of Ernest Optic, who is in fact, both Alpha and Optic have asteroids named after him because they were so famous. Optic was a mathematician, and he went, and this is how he calculates out what the Roche limit is, from here to here, what the radius is. And it's some kind of a constant times the radius of Earth times ratio of the density of the Earth to the density of the Moon to the 1/3 power. And the Roche limit is primarily dependent on the density ratio over here, not the moon size. And the radius of Earth is usually used as a current radius, which is not correct for a smaller initial radius of expanding Earth. I always look at these things and say, well, the Roche limit would be out here, but if the Earth was smaller, then the Roche limit would be closer, and we could have a body that's approaching it, and it's not going to break up according to the Roche limit. Now, the Roche limit is kind of interesting because if you go out to Saturn, the rings of Saturn are actually inside the Roche limit. And that's why they're rings, because they could not gather together to actually form a moon out there. Now, the formation of our moon, there's 4 theories I'll go through. One is the barbell theory, which James Maxwell proposed. The Earth and Moon were ejected from the sun and separated later. There's the fission theory, which is the Earth was hit by a body that ejected mass into orbit to form the moon. Earth orbit accretion theory. This is where the moon and the moon was going around the Earth, and both of them accreted, grew in size from material orbiting the Earth. And then there's the Earth capture theory. The moon was formed separately and then captured by the Earth. Now, the barbell theory, pardon for my illustrations, this is envisioned basically as a blob of hot gases connected to another bigger blob of hot gases rotating around like a barbell. And the centrifugal force spins off this barbell shaped blob. The whole thing got spun off from the sun, and it eventually ended up in Earth orbit. And then they separated to form the moon and the Earth. But there's some problems with this model. One, it's based primarily on the similarity between the Earth and the moon from the standpoint of geological considerations. This is many of the same. Now, this is not always. The moon and the Earth have definite differences in the materials they're made of. The Earth is very rich in metals and the moon and volatile substances, and the moon lacks these. That's why the moon doesn't have much of a magnetic force at all. But the Earth is, the composition is different. And this, what I've found on this is, if you look up documents, like on Scholar Google.com, you can look up documents of papers and get papers that were written by people that studied the moon rocks when they came back, who worked for NASA or they were hired by NASA. I mean, they might have worked for the University of Chicago in some labs or other places. Another thing against this is it tends to violate the laws of orbital mechanics. You don't end up with two things like two blobs of something just turning around in space. And the Roche limit would break up the moon as it's separated, so it would fragment it. And also the formation of other planet satellites, if this would be very problematic to try to figure out. Now, the fission theory is where a Mars-sized body hits the Earth, ejecting material to create the moon through orbital accretion. Now, once again, this material that would be fragmented or come up will go through the Roche limits. And when it goes through a Roche limit, it's going to go and be still fragmented. So you'd have to have the moon accreted outside of the Roche limit. And the problems with this is, where did the other body come from? Now, I've been explaining, how the planets are formed, but where would this other body come from? I mean, are you just wandering around someplace? And why wasn't the other body just captured by the Earth? Plus, if the other body was big enough, if this was fast enough, it would the Roche limit would really have problems, cause accretion problems. And this would have to happen early, like 4.5 billion years ago, because we have solids that we found on the moon that I believe are 3.5 to 4 billion years old. And whatever happened to the other body? And a lot of this material, if this happened, would just be lost to space. I mean, it wouldn't even be necessarily be in a plane where it could form as a moon here. And some people have said that it might have come from the Pacific Ocean. Well, the Pacific Ocean, according to James Maxwell and others, is a maximum of 200 to 250 million years ago. And so there was no Pacific Ocean where this would have happened. Okay. Now there was the Earth orbit accretion theory. And this is that a much smaller moon was formed in orbit around a much smaller Earth, and both accreted together. Accreted just means the particles gathered to make them together. There's less problems with this than with either the barbell or fission theories, but there are problems with this model. The Earth and moon have different composition, yet accreted in the same relative environment. And where did the embryo moon come from to begin with? It could be regarded as a less probable subcase of Earth capture. Both of them accreted in orbit. Now, in this Earth orbit accretion, basically says that the moon was in orbit around the Earth when it grew in size, the same as when the Earth accreted. But it's very similar if it accreted in orbit around the sun and we captured it. They're very similar cases. Now, the Earth capture theory, this is where two protoplanets form in slightly different orbits, about 1 astronomical unit from the sun. That's about the distance we are away from the sun. Now, there's nothing to say in one of those jet streams that you only need you could only form one body in it. It's very possible that other bodies could have been formed in the exact same jet stream, but there are different positions in it, and they're moving around. You're the same distance out, or relatively the same distance out. You're moving around about the same time around the sun. So they both could have accreted. I mean, the moon could have accreted in the exact same way that the Earth accreted. Now, Opic showed if this happened, the larger is kind of a coin flip of which one would be larger, but the larger one will grow larger relative to the other. And the larger one will get more metals and volatiles. Now, some of the people who have studied the materials that have been brought back from the moon have favored this thing. I mean, this is the rich get richer is a quote that I saw that was quoted from one of Opic's things, and they said this is exactly. I mean, what we're seeing with the moon rocks compared to the Earth composition is exactly what would happen in this case. And capture is possible on a slow basis. I mean, it's not the moon would come in and it would just be captured immediately and wind it down around the Earth. And one of the things with the reason why I mentioned earlier Triton and the moon and about a dozen other bodies, other very small satellites, are peculiar in our solar system because they're retrograde. In other words, most satellites, if the main body, the planet, is rotating in one direction, the satellites are going around in the same direction. But the moon and Triton, which is Neptune's satellite, are both in retrograde orbits. In other words, the moon is going around in its orbit opposite to the rotation of the Earth. And it's very hard to get something in a, this is one of the things like the barbell theory. I mean, if they're both going around, how do you get, I mean, you're violating laws of physics if you try to take something that is in a prograde orbit and try and go into a retrograde orbit. And Alphen's analysis showed that our Earth should have had about 5 or 10 moons, and the number he doesn't know, but with the jet streams that formed around it, it should have had about 5 or 10 moons. And furthermore, with the moon being captured in an orbit, whatever moons were there before is very possible that our moon cleared them out, and many of the craters on the moon are due to the moon gathering, these smaller moons, just having them crash into it. Now, it's improbable that the moon capture would occur on the first encounter. The first encounter, however, would change the moon's orbit. And what happens is, here's the moon had one orbit. I mean, they're about the same distance from the sun. But the moon would go and pass, and it would change, the Earth would change its orbit. And now the moon's orbit would come close to the Earth twice in a year. And each time the orbit would be changed a little bit smaller, a little bit closer in, until finally it was able to do the capture. So this is the theory that Alphen proposes, and it is, to me, it's most logical. He goes into the mathematics of how this works. Now, if you take the sun and regard the planets as basically satellites of the sun, and then you go down to the same procedure, you'll find that the satellites of each of the bodies tends to fall right along this theoretical line, except for Mars, which very well could have been asteroids. Alphen feels that there's a very good possibility they were asteroids that were claimed, and Triton and our moon. They are the closest to actually being planets. And both have retrograde orbits, both seem to be go into this, were captured by Neptune and the Earth. And accretion isn't necessarily a cold process. A lot of times people think, well, you have these particles that come together in space and secretion, but you end up with the kinetic energy, especially as the particles get bigger and bigger and get into boulder size and what have you. And so Alphen and Aramis worked out, and they now this is a scaleless, dimensionless y-axis, but they estimate that the Earth could get up so it was molten and extremely hot. And then finally, after the accretion stopped, it came down to the temperature that we have today. So considering that the Earth was molten, like you always see with the pictures, you have the molten volcanoes, the Earth was all lava or whatever have you. It actually, and by the way, one of the reasons why this interested me is that my friend James Maxwell always told me, he said, well, I don't believe in cold accretion because there's certain minerals on Earth that you need to have a hot environment in order to form them. And this is exactly what I mean from the accretion process, because of the energy has to go somewhere. And if you have two things bang into each other at a pretty good size, you create heat. Okay, now I'll get into expansion tectonics a little bit and show how some of these things fit together. One thing, I don't think, hold on one second. I'm trying to see if I have that slide. No, I don't. I didn't have the slide, but okay. Well, I'll skip it. Says I don't have it. Okay, is the Earth expanding? The answer seems to be yes. This brings up two questions. One, what is the evidence in favor of expansion? What mechanism is causing the expansion? Now, I'm kind of interested in what mechanism is causing it, but evidence in favor of it, yeah, it's if you look and do recreations of the surface of the Earth, like James Maxwell did, where he took away little time slices and the Earth came, all these pieces kind of fit together. And it's like a crossword puzzle. If I gave you this crossword puzzle and said, hey, go and I took all the pieces apart, put them together, it's kind of hard. Why is it hard? There's no pattern to it. However, what if we added a pattern? And then we looked at a couple of spots on that. And here's our pattern once again. And you can look at this spot. Okay, this is great. Look at now if this piece and this piece fit together, it's almost like if we had, let's say an animal, or if we had an ore deposit, and the ore deposit was on this piece of land, which was widely separated from this one. If we could fit it together, we say, hey, that's a pretty good fit. These probably were together in the first place. And the same thing over at this junction. Here we have one piece that's in 1, 2, 3 slices. This is in 2 slices. Here we have a shadow. In other words, if you have putting together the expanding Earth, it's like putting together a puzzle, but you have to do it in reverse. And this is exactly what James had done. And he did a fantastic job of it, and he's taken it all the way back. And there's other people too. Let's see if I have. What you want to do is you want to look for unique features. And a unique feature I define as a feature like this, where you have 3 different land masses, and all of them have like the same mineral deposit or some common unique feature. Oops, sorry about that. Don't know my right click from my left click. Okay, so what you want to do is you want to look for unique features. And the higher the confidence level, the more convincing the evidence is for that. Types of features that are presented, this is partial. Well, a lot of other people have done this. If you remove the oceans early on, you can go and you can remove sections of the ocean floor. You can do paleomagnetic reconstruction, geodetic data from satellites, mountains, rifts. There's a lot of physical reconstructions, but also there's a lot of biogeographical ones too, like trees and fauna and plant distributions, fossils, where the fossils are in locations. An excellent, I guess, is a book. There's a book called Here Be Dragons by Dennis McCarthy. And he goes and shows on the Pacific Ocean, he calls it the zipper effect. And you see you remove the Pacific Ocean and bring them together, you'll have one maybe fossil found in adjoining places. Same way if you do the same thing with the Atlantic Ocean. Now, what causes Earth expansion? Samuel Warren Carey was very interested in this. In fact, he spent most of his life trying to find this. These various people have come up with theories. The famous physicist Dirac even came up with one. And one was a pulsating Earth, mass increase due to meteor or asteroids striking Earth, massive core that decreased the density over time. But if you did this and you calculate out what the density was back when before the Earth started expanding to what it is today, you find this, you have to have a density that's 50 times what it is today. So it's, what is it, a neutron star? Somebody proposed neutron stars in the center of our thing. Gravitation has changed over time. The gravitational constant has. The mass of everything in the universe is increasing. Seems to me that all of the above are too esoteric. Anyone can come up with a theory, but is it backed by empirical laboratory experiments? Okay, Alpha inspired my path. When I was writing my thesis, I was studying Alpha's plasma and magnetohydrodynamic concepts. Why not think in terms of electromagnetic forces rather than gravitational forces like Alpha did? New mass requires protons and electrons. Both are extremely small. They're about a 10,000th of an angstrom. Now, an angstrom is 1/10 of a nanometer, and a nanometer is 1/100000th of a meter. So this is a pretty small particles. All the matter and everything we're made up that we have around us made up primarily of protons, neutrons, and electrons. But these particles are so infinitesimal. 10,000th, it would be 100,000th of 1/100000th of a meter. Electron conduction occurs, so why not proton conduction? And we know in the Earth, electron conduction and wires and things. A little research revealed that proton conduction does indeed occur in both solids and liquids. And it turns out that ice and water and the minerals that make up the magma in the mantle of the Earth, they're all excellent conductors of protons. In fact, there's been a lot of research done on this. And it had been proposed at one point that because you have E equals mc squared, doesn't mean that you can condense matter into energy. Now, my hypothesis that I came up with was electrons and protons, primarily from the sun, can be the source of a mass increase causing Earth expansion. No, we live in an electric universe, and the first half of my talk has all been about the electric universe with the plasma universe, which is essentially the same thing. The sun provides an ample source of both protons and electrons. The Earth's magnetic field has a magnetic field that captures these particles, which is different than Mars. I mean, maybe is very conceivable that Mars never underwent any expansion because of the lack of a magnetic field. High energy particles are in the ionosphere. There are also massive radiation belts surrounding Earth, which captures particles. The Earth's magnetic field has sufficient force potential or electrical potential or magnetic forces to move these charges all around the place. And now this was an observation that I made, and I don't know whether it's correct or not, but I throw it out there. It seems like most of the expansion of the Earth has happened in the last 500 million years. And before that, there was very little. For the 4 billion years preceding that. And I was looking for some type of a correlation. And the only thing I could think of that really correlates is the amount of water on Earth's surface. Well, the amount of water is a proton electron conductor. It is on the Earth, the amount of water seems to grow in proportion to how the Earth has expanded. And so I hypothesized that one of the things we should keep our eye on and deserves looking into is the fact that does water kind of mirror the growth of the Earth? Now, there's some unanswered questions. Well, you have protons that are plentiful in the neighborhood of the Earth, but most of the ones that are captured in radiation belts or the ionosphere are quite high energy and collide before hitting the ground. They never make it to the ground, even over the poles. Some of these high proton energy, when they get up really in the high energy, they have multiple collisions with particles before they hit the ground. And free protons tend to capture electrons, so they don't stay free for long. However, we live on an Earth where electrical potential differences produce currents almost everywhere. Lightning produces ionized particles nearly continuously worldwide. The fair weather current, I'll get to this in a second, transports charged particles to the Earth's surface from the ionosphere. And with the sun, we have almost an infinite supply of both electrons and especially protons, no shortage of raw materials. And here is Earth's surface is like a big capacitor. You have the ionosphere up here and the surface of the Earth down here. And with a capacitor, there's a dielectric that is a dielectric basically is an insulator in between the two, and the air is an effective dielectric. Breakdowns occur via lightning hitting the ground about 8 million times per day, or about 3 billion times a year. And the figure that I've heard quoted is 100 times per second. Now, when lightning hits, that's plasma. That's hot. You're talking about currents 50,000 to 100,000 amps and more. That ionizes everything. And of course, with the ionization of it, you get protons. Plus, you have what's called a fair weather current. Now, here is where you have a thunder cloud and you have lightning strike, and actually you have what they call sprites going up on top, from the top of the cloud up to the ionosphere. But with fair weather, you end up with particles, positive charges coming back to the surface of the Earth, which is negative. And even with the cloud, you end up with some positive charges coming back. Now, actually, the potential, if you're into it like electrical type stuff, the potential between the ionosphere and the surface of the Earth is about 200, 300,000 volts. If you're a 6-foot person, let's say, and you're standing, the electrical potential between your feet and your top of your head is about 200 volts.
John, I just want to make we are over at noon, or noon our time. So, do you think you can wrap it up in a few minutes, so we'll have enough time to just?
Yeah, I'll try to wrap it up. I'll go look.
Otherwise, what will happen? We will have no time, and because I do have a time limit on this. So.
Oh, okay. Sounds good. We'll do.
Okay, just letting you know. Okay. Thank you. All right.
So you do have particles, charged particles, moving everywhere, and there's plenty of particles to accommodate this. So the questions we ask: how can electrons and protons create new atoms within the Earth? And what is the mechanism involved? And nuclear fusion is where you have two nuclei joined together, and in doing so, it's just like with a hydrogen bomb, you end up with with energy. Most of you probably know what nuclear fusion is without anything. A few things to keep in mind. 94% of the Earth is only 4 elements. And another 4 elements, you're up. So all the 90 natural elements are only like 0.9%. Fusion generally results in an increase of energy. And to have fusion, the biggest problem you have is the Coulomb barrier. For 60 years, they've been trying to tame fusion because of this doggone Coulomb barrier. Now, what the Coulomb barrier is a proton is positively charged as it comes in toward the atomic nucleus. So it will repel each other just like 2 magnets do. And the only way to accomplish this is to accelerate a proton to high energies. This is why with the hydrogen bomb, or where you're trying to accomplish fusion, you have to have such high energy levels, or you have to take a proton and just pump it up to an amazing thing. And this is called hot fusion. And the Coulomb barrier, this is potential energy. Here's the nucleus. And it will, because of the Coulomb barrier, the positive nucleus and the proton coming in will repel each other. Unless you have tremendously high energies and get over this barrier, then the proton will come down and fuse with the other nucleus. Cold fusion is attainment of fusion at essentially room temperatures. It's very controversial. I know this, but it's been repeatedly shown to occur experimentally in labs throughout the world. The United States and other governments have put millions into this doing. And by the way, the literature out there is a ton of literature. I always thought that was a pseudoscience, but it's not. There's no generally acceptable theoretical mechanism to accommodate or tell how you can overcome the Coulomb barrier without having very, very energetic protons. And the way to tell it by happening is excess heat is produced and byproducts of fission are found, like tritium. Tritium, that's a radioactive isotope of hydrogen with only 12.3 years half-life. And it's found in some cold fusion experiments that tritium is produced. And also the ratio of helium. Natural helium is 99.9999%. And helium-4 with an extra neutron in it is very, very small. Both of them are stable, but in nature, you end up with a much different ratio, because helium-4 is produced as a byproduct of nuclear fusion. So if you're looking for either tritium or the helium ratio, and they've conducted experiments, I won't go into this right now, but they've conducted very controlled experiments. And what you end up with in cold fusion, you end up with transmutation, it's changing one element to another by a radioactive decay, nuclear bombardment, or similar process. Nuclear synthesis is the formation of atoms which are more complex than a hydrogen atom. And this is what they did is they used a palladium electrode, and this dark line here comes up, and this is what it originally was. After undergoing this cold fusion, they actually went and they ended up with all kinds of other elements that weren't in there being produced. And there's fusion evidence within the Earth. Certain hotspot volcanoes like Kilauea and Aceto, I guess, is in the Galapagos, have yielded tritium presence and helium ratios much higher by factors of tens of hundreds than the shallower crustal volcanoes. And in volcanic lakes, where the bottoms don't mix with the gases are trapped down there, they have from the bottom have found presence of tritium and high helium ratios strongly indicates tentative conclusion that fits with the hypothesis that what would be expected if fusion were occurring within the Earth. In summary, basically, we've gone over Alfvén's comments of a plasma universe, how the solar system was evolved, how our moon was formed as a captured body, touched on some evidence of Earth expansion. My hypothesis that electrons and protons could explain the mass gain of the Earth, resulting in expansion through cold fusion. And I come back to Occam's razor, which basically says, if you have a lot of theories out there, what's the simplest one? And all I say is that we have electrons and protons all around us coming in, and I think it's the simplest theory. That's it.
Well, listen, thank you so much. I'm sorry we had to rush at the end there, but it was totally fascinating. I think one of the things is the actual formation of the solar system, the planets, and all of that are a really neglected part of science. Don't you feel?
Oh yeah. Well, there's been a lot of research done. If you have to go in and dig, but there's a lot of people out there. At first, when I read about this accretion of bodies, it seemed like it was not a whole bunch of interest in it. But recently, I've been seeing more and more people coming in and talking about accreted bodies. So it's
Yeah, and I have a couple of questions, but I'm going to try to get some things from the audience. It says, "I like growth and expansion by cold fusion." Now, one question, especially at the end there, you were talking about cold fusion. Are you talking about cold fusion or regular fusion?
well, it would be cold fusion. The difference between it with regular fusion, which is hot fusion, you have to take the protons and get them going extremely energetic in order to overcome the Coulomb boundary. For some reason, now there's been several theories proposed on why cold fusion works. And if you read the literature, they'll have like the same exact palladium electrode, and if they do 10 experiments, in 6 of them it works, in 4 of them it doesn't. So,
Sure.
there's an art to it as well as a science, and there's no generally accepted theory that how it works. But for some weird reason, you end up with this fusion at regular temperatures, and it's just what you do is basically an electrolysis type thing. You get it started with that. Sometimes they have runaway fusion. It's not like a hydrogen bomb, but they'll go and they'll actually melt the containers that the fusion is occurring in. And it's once again, it's an art as well as a science.
Right. Well, a lot of times our technology, people tinker and we can manipulate things without really knowing what they are. I mean, we manipulate light all over the place, and yet we don't really have a real good model for it.
The classic example in my mind of that is in 1803, Wollensak found dark lines in the sun's spectrum. And for over 100 years, people used these dark lines. Even Fraunhofer used it to tell the quality of his glass, and he had came up with 576 or something like that, dark lines. But it wasn't until the electron was discovered in 1897, and then Niels Bohr in 2010 or 2011 came out with his model of the atom, that we knew that when electrons either get energized or give up energy, popping to different orbits, you end up by getting out these different frequencies. But for 100 years it was used. But
Right. Here's the answer to the question. UNIVAC 1103.
Yeah, 1103A. I think
I don't. Oh, there's A or B. Listen to a guy. I'm going to have to get my dad. I got the answer from him. So, okay. Let me ask.
1105.
Oh yes, 1105. He had the early version. He had the beta. I don't know, but another. I have a question. You keep saying on my thesis. Did you write a thesis, or are you just saying in general a thesis?
I wrote a thesis.
Now the thesis was for university or your own?
Oh, for the university here.
Oh, okay.
Yeah,
and what was that thesis about?
Well, I go over 3 paradigms in science. It's basically I dissect paradigm shifts. And I go over Hubble, who is attributed with the expansion of the universe. And Hubble never thought the universe was expanding. He did not believe the doctor stuff. I go over Alfvén and some of the same stuff I've gone over here. And then I go over Carey. And what I what I tried to study was here's three paradigms that would change our way of. We have to rewrite textbooks, but they've got caught into paradigms, and they're
Stuck.
Yes, they're stuck.
Now, let me ask you another question. I'm going to keep moving these things along because we've got a lot of. Is that thesis in a university or where was it?
You can get it on.
I mean, where you said it was involved with a school?
University of Arkansas in Little Rock.
Okay, and what year was it?
2015.
Okay, so very soon. Oh, very early.
Yeah,
well, at least you know.
You can get it on Maxwell's.
Okay, Expansion Tectonics.
Yeah.
Okay. Well, for an 81-year-old, Mr. Eichler is cool, good energy. So there you go. I always like to put those things up there. So in general, a general question I have for you is obviously you came to the conclusion through your work about the guy who wrote the book. I can't remember his name. That you showed lots of. Is that book available?
Alphen's book?
Yes, Alphen's books.
Oh yeah, you can go on Amazon.
Okay, Alphen's book and available. I would
also if you search for the title of it is SP 345 or something like that. If you search for the title of it, you can download it. It's available on NASA's website, and there's several PDFs out there that you can get.
Oh, okay. So it is actually
widely available. Yeah.
Okay. Okay. So it's called
500 or 600 pages long. Huh?
Oh, okay. I see. Oh yeah, okay. I think I can, let's see if I can share this here real quick. I did find something like that. So this here, it's SP 345 in the NASA Historic Office. So okay.
345. Oh, did I remember it right?
Yes, you did. Oh, I mean, you're 80 and you are fine and dandy. So I was getting back to my question.
Yep.
When was it in your studies? Because obviously, I think this guy's book, Alphen's book, is really fascinating because it really, I mean, it gives a real possibility of how the solar system formed, and I think that's just such a neglected area. And I'm gonna.
It's done by a physicist who is
won a Nobel Prize, right?
Pardon?
Didn't he win a Nobel Prize?
Yeah.
And he in his speech says it was partially wrong. I mean that's pretty amazing. I'm going to get to my question. When in your career of looking all of this did you get into the expansion tectonics? Obviously, that
was absolutely by accident. When I was in high school, I went and was very interested in science, and so I would read everything that I could possibly get my hands on. And when I got into college, I was intending on becoming a theoretical physicist. So that was kind of I got into computers completely by accident. But one of the problems, in fact, I'm writing a book. I've got the thing, I've been writing it for a number of years, and it's almost ready to put out. It's called an Infinite Universe. But when the problem that I've always worried about or wondered about is you have so much energy being liberated from the stars. How can you if you're going to have an infinite universe, you have to have some recycling process. And so one of the things I was thinking about was that photons, as they're going through space, experience a red shift, which is a loss of energy. And the loss of energy, they get longer and longer in wavelength. So I thought, well, maybe those are penetrating the Earth and heating the Earth up. I didn't know anything about geophysics, geology, or geophysics primarily. So I went down and got some books on that. And I started looking at it. And in one of them, they had Alfred Win, the guy, the continental drift guy, WENG. I forgot how you spell. But anyway, they had a picture of his, and this picture showed the Pangea, and before the breakup, he had three pictures. Mm-hmm. And so I saw that, and it looked oval in shape, and I thought, my gosh, could it be that the Earth expanded? And then I went for, I for 15 years.
What year was this?
1958.
Whoa, wow, back there. Wow.
And
Young
so
man then.
then for years I would go over the research institute. People think I was Looney Tunes. I mean, when I'm talking about this. And so finally I ran across Curie by Curie's mentioned in a 1974 book. I wrote to Curie.
Wow.
I told him my idea with the red shift and everything, and his seminal book, The Expanding Earth.
Right.
He mentions one paragraph for me. You go to the back for the
Yeah, I remember. Yeah, I saw your name. I saw your name there because I bought every book I could on Expansion Tectonics, Expanding Earth. Yeah, and that's how I saw your. I think that's when the first time I saw your name.
Yeah, but so I've been thinking about this, and then with Alphen, I ran across that book because I was interested in Infinite Universe, and ran across that book and Alphen's work. I mean, it all comes together just like that puzzle. All the pieces begin to come together, and you begin to see it. And now I'm probably stuck in my own paradigm.
No, it was fantastic. Again, as this person said, at my 80, would like to be as clear as you speak. There you go. I mean,
well, thank you.
well, listen, no. So sincerely, I mean, this has been a very stimulating. Like I said, I'm going to buy Alphen's book. So one of the
download is
yeah, download it. Yeah, absolutely. Yeah. And you mentioned several times now infinite universe, meaning in the sense of it's infinite in space. Is that what you say?
Space and time.
In time.
Space.
So you are another person like myself and many, many other critical thinkers who just don't have this idea of that somehow there's a finite universe. It's the size and it's expanding.
No, in fact, even Hubble. I mean, that's what bothered Hubble. Hubble wanted a nice, stable universe, something that was.
Wait a minute, is this the Hubble who's responsible for his work spawning the Big Bang?
Yeah.
So the guy who started it doesn't believe in the Big Bang.
Oh, he spent 25 years until he died in 1954. Hubble went, and it's fascinating. I mean, I've got several books of his. He spent the last 25 years of his life. He didn't believe he would always say, if you believe the red shift was accounted for by Doppler, then that would happen. But he thought that was not a stable type of universe. And he spent 25 years of his life trying to figure out some type of measure that he could positively prove that expansion wasn't happening.
Right. Yep.
And everybody attributes the Big Bang to him. He did.
I know. Isn't that bizarre? I mean, that's so bizarre. And if you look at most people, here's another person, Michael Clark. Yes, infinite in space, time, and distance. I mean, it just doesn't make sense. The moment you really start thinking about it, then your critical mind, if you really spend the time and say, okay, I'm open. What are the possibilities? The idea of this finite space is interesting. The other thing too is interesting. My father and another person actually not calculated, but looked at the gravitational field of a galaxy. And you had shown. I told my father, who lives with me in the next room watching here. He had that those velocity of stars. And what he said, and he gave a talk at one of our conferences, is, look, you can see the arms. You can see the gravitational field in this. It's not uniform. And I also, on Dissident Science, my channel, I did a very nice talk, one of those scripted talks with graphics and all that, about they found two universes without dark matter, and they were spherical. Of course, there's no extra anything there. It's totally predictable by a point. They use point masses. So it's interesting to me that you too do not subscribe to dark matter, right?
Oh, no. Well, the thing is that you have to, if you assume the universe is infinite, then there's some other things that go along with that. In other words, it's not, you have to have what I term no one-way streets. If you have some phenomena which is happening, that phenomena continues, like the light doesn't get recycled. If it doesn't do that, then the universe can't be infinite because it's going to run down.
Right,
It's a
right.
little bit of
No,
a
yeah.
philosophical
No, it
thing.
is. Believe me, that's one of the things people, I think, don't realize how much philosophy is involved in science, in physics, especially.
Well,
Especially,
yeah.
yeah,
Well,
because especially we're
Einstein,
looking.
the thought
Yeah, go ahead.
experiments and stuff. No,
Yeah,
like with Einstein's thought experiment, yeah. You go and you have a feeling for something, and it just doesn't sit right, and you begin to look, look.
right, right, right. And I think another thing about your work that strikes me, and which is one of the things that the more modern theories are looking at. My dad and I have our particle theory, where everything in the universe is a mass that results from a mass that's moving. Everything. This
Yeah.
idea that you have magical things going on, or ultimate particles that organize themselves magically to form the universe. I think we're starting to see these things just don't pan out. So
Well,
it's
look, you have that book of that Stephen Harrell. Uh,
yeah, right, right.
okay, look at the.
Yeah.
Did you read my at the
Oh, of
very
course, of
at the
course. I
very
read the whole.
at the very last page?
Yeah,
Yeah, there you go. At the very last page of mine, I
right,
say, even, I mean, I'm talking about second law of thermodynamics,
right,
and I said, even if everything was just like a gas, the whole universe ran down, the particles still would be attracted to each other by gravitation. They would still have electrical characteristics of that, and they would reorganize themselves.
right, right. Yeah, I say yeah. For those, if you want to read more about it, in fact, it's got a great bio, and this is something that Stephen Hurl did that is just fantastic. I mean, this book is really gold. What he did. I mean, because you guys aren't in universities where you should be teaching this stuff. At least we have a really good history there. And I recommend this book, of course, if you want to read more about John Eichler and his work. And then because you talk about the electrical part of the universe, obviously, and you say there's a gravitational part, there's an electrical part. Is that what you say?
Right, right. Well, like with the solar system, what you end up with is you do have gravitation, but then
Right,
if you have charged particles, you have
right,
an electrical part too. And
right.
as Alphen's famous last words when in his Nobel lecture were, "And in the beginning, there was the plasma." He
Yeah.
says that 99.99999% of the whole universe is plasma.
Yeah. Well, I think the most important thing is that we're really getting to know people like yourself and your work, getting that out there. I mean, this has been thoroughly enjoyable. I think what we probably have to do is bring you back and maybe have a topic and discussion. I think there's just so much that you brought up in what you presented to us today. I mean, it's really gold for those people who don't know about it. I really wasn't familiar with Alphen's book. To take a look at
Oh,
that, and maybe
to me, Alphen was one of the true geniuses of our last century. I mean,
yeah,
and he just got interested. He's from Sweden, so he saw the
right,
Northern Lights. So he started studying the Northern Lights up there with other scientists that were studying them. And other guys were so theoretical, but Alphen did everything according to lab. And
right.
if it didn't work in the lab, to hell with it. I mean, it's I'm not going to
Oh,
pursue that.
right. Well, I think it's absolutely remarkable because I really didn't know about him and his story, even about the Nobel Prize, him basically almost going against what he got the prize for. That's so unheard of because today and age, what you have is I don't know if you've had did you read the Higgs fake by Alexander
No, I
Unsker? You should take a look at it because it's truly reveals the opposite of what you're talking about, which is using real
yeah.
laboratory evidence. How they go about pretending to find their particles
Oh yeah,
is
yeah,
insane. I mean,
yeah.
they literally take programs, computer programs, and they write filters out for what they found before, not justifying that in the first place, and then saying that this isn't noise, this is the real signal. I mean, if you were to take yourself or myself or my dad, real engineers, or anybody from NASA, real engineers, and took them and sat them down in the control room of the Large Hadron Collider and have them analyze their engineering and software techniques,
Yeah.
I mean, it would be abhorrent. I mean, it would be the people would go away with just horrified, and yet no one knows about that. No one talks about it. We continually, people continually support this stuff. We throw billions of dollars at it.
Oh yeah, yeah. People are locked in paradigms. You can't shake them loose. But see, that's one thing this one thing with the expanding Earth. Now there was some geodesic data that was analyzed by Harrelson, and I don't know what the other guy's name was, back in 1991, and it covered
Right.
like 1975 through 1990 geodetic data from satellites. And they actually, and James Maxwell probably went into this somewhat. What they did is the actual data, if you look at it, shows some growth, but they
Right.
thought that was noise.
Yes, I know. Right. Right.
But the thing is that unlike a lot of these other subjects, the expanding Earth over the next 50 years, 100 years, some people will say even sooner, they're going to come to irrefutable evidence.
Of course.
That the thing, and then there's, I mean, but that's one of the few things. I mean, you can't talk about dark hole, going to dark hole,
Black hole.
a black hole. Yeah, you can't do that. But here on Earth, we can. But you can't go down very far. You can only go down about 40,000 feet.
Right. Of course, you can't. You can't.
And so you don't know what's inside there. You just have to look at the seismic data that comes through. But
Right, right. Well, listen, we're going to have to really stop here, but I think what we need to do is I want to get together with you offline, and let's think about a time where to get you back. And what we'll do is maybe we'll think about something that you've talked about, because you've given so much in this talk. What I'd like to do is give our audience a chance to interact more with you today, and
Sure.
it's a great way for us to bring you back. It's a great people to have, as we say in Portuguese, they put agua na boca, water in people's mouths, to get them salivating for something to be able to talk with you, because I think you brought up so many things. But I would really recommend everybody check out, if you haven't read about Eichler, and you're coming up with a book. You can get this book and read about your work and what you think about all this. Also, to get Hans Alphen's book, it's online for free. And you said you're writing a book, is that right?
Yeah. I'm
Okay.
I started back in I think it was 2007, 2008, and so I've been I took a year for a what do you call it? A kind of a special study.
Sabbatical.
No. This was down at the university.
Oh, okay.
And I got one of the professors in the rhetoric department. I said, can will you give me independent study for a year? And he said, I don't even know you. So I took a course from him, and afterwards I worked with him for a year, and I got most of the book written then. But then I got off into some other stuff. But I've got it. It's like 450 pages long or something like that. I told Stephen that what was in that book that you have right there,
Right.
I would like to put that as an appendix in my book. And so he didn't want to, there you go. He did not want to have me do that and come out with my book right away. So I've been holding off until, so I've got to get my rear in gear and get back on that thing, because that's one of the one of the books. And tell your dad that I also have started on a book about computer architectures, because I was
Oh, wow.
I was a systems programmer. I've for 14 years, aside from programming like operating systems and stuff like that,
Right.
designed computer systems. And so there's a lot of very funny anecdotes that I have.
Right.
Your dad and I probably get a great time in talking together.
Oh yeah, no, I for sure. Just the stories with that. But listen, I want to thank you again, and we will definitely bring you back. And I've had numerous people say that. They said bring you back, so we will do that. I want to thank you for your work, for everything you've done over the years. It shows real critical thinking, and that's what we need. I'm really fascinated how all these amazing minds I've met over the years, over the last 3 decades, have all come to many similar conclusions. Infinite universe, the Earth is expanding from so many different angles. I mean, Hurl comes from dinosaurs. You came from looking at the evolution of Alphen's book and all your work. It's quite fascinating. So I do want to thank you so much, and we'll invite you back. And I'm going to wrap this up then.
Okay, well, just ask your dad one thing for me.
Yes.
Ask him on the 1103 if he remembers what instruction a octal 45 is.
Now, he was a hardware engineer. He wasn't software.
Oh, he wasn't? Well,
No. But, he at that point, he's always joking with me. He says, software is just, writing programs. It's the hardware that does the work. So
tell him I've done both.
But I'm sure he may know, but we'll get together for sure on that. So, all right. Well, thank you so much, John. I'm going to bring you down and wrap this up. Okay.
Okay. Sounds good.
Okay. Thank you very much. Take care. Well, folks, that was just absolutely amazing. We've gone over 10 minutes, but it was well worth it. We're going to be having him back. And remember, we're going to be having next week, we're going to be having the infinite universe theory with Dr. Glenn Borkert, another great mind. It's just wonderful to be able to talk to these people. And after that, we're going to also have Alexander Unsker in January, sometime next year. The author of The Higgs Fake and Einstein's Lost Key. And also we'll be having Nick Percival, who is from Harvard, but is one of the experts in special relativity and all the problems with it. So I want to thank everybody once again. And remember what I always say, I'm Dave D. Hilscher. I'm your science therapist trying to get you the promised land of becoming critical thinkers. Stay critical, stay thinking. Ciao for now.